There was a moment 13.8 billion years ago before which the word before may not have meant anything at all. Try to hold that sentence for a second, because it is not a poetic flourish. It is closer to a literal description of one of the strangest conclusions modern physics has ever reached. Time itself, as best as our current understanding of physics can determine, appears to have had a beginning. Not a beginning in the sense that something started happening at a particular clock time, the way your day began this morning. A beginning in the sense that time itself, the very dimension along which cause leads to effect, along which one moment gives way to the next, appears to have come into existence, along with space, along with everything else, in a single event that cosmologists call, with a certain deliberate plainness, the Big Bang. Here is what makes this different from almost every other scientific story we have told in this series. We are not talking about a distant object, sitting somewhere far away in space, that we can point a telescope toward and study more closely if we wish. We are talking about the origin of space itself. There is no over there for the Big Bang to have happened in, because space itself did not yet exist to contain it. There is no earlier context to place it within, because time itself, as we understand it, began there. This should feel disorienting. It is meant to. Every intuition you have ever developed about beginnings, that something existed before them, that they happened somewhere, that there was a moment leading up to them, may simply not apply. And yet, unlike so many of the deepest mysteries we have sat with in this series, the Big Bang is not merely theoretical speculation dressed up as science. It is one of the most thoroughly evidenced conclusions in the entire history of physics, supported by multiple completely independent lines of observation that all converge on the same extraordinary story. The universe had a beginning. It happened everywhere at once because there was no elsewhere yet, and we can trace its history with remarkable precision back to a fraction of a second after it began. A fraction of a second after. Not the beginning itself. That distinction, small as it sounds, is the entire second half of tonight's story, and it holds one of the most humbling admissions in all of science. Let's begin with the two men who found the leftover light. The whisper still travelling through the universe from that very first moment, discovered almost entirely by accident, in a receiver they were trying to clean of what they assumed was ordinary interference. In 1964, at Bell Telephone Laboratories in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were not trying to discover the origin of the universe. They were trying to solve a much more mundane problem. They had access to an unusually sensitive radio antenna originally built for early satellite communication experiments, and they wanted to use it to study radio emissions from our own galaxy with greater precision than had previously been possible. Before they could begin their intended research, they needed to calibrate their instrument carefully, eliminating every possible source of background noise that might interfere with the faint signals they hoped to measure. They found a persistent hiss, a low-level static present in every direction they pointed the antenna that simply would not go away no matter what they tried. They checked the obvious sources first. They pointed the antenna toward New York City, thinking it might be picking up radio interference from the metropolitan area. The hiss remained, unchanged. They considered whether it might be residual radiation from a nuclear weapons test that had been conducted in the upper atmosphere a few years earlier. The timing and characteristics did not fit. They climbed into the antenna's horn structure itself and found a pair of pigeons nesting inside, along with an accumulation of what Penzias later described, with careful scientific understatement, as white dielectric material, pigeon droppings. They cleaned the antenna thoroughly and removed the birds. The hiss remained. Exactly the same, in every direction, at every time of day, in every season. Penzias and Wilson were, by this point, genuinely puzzled. The signal was faint but completely uniform, coming from every direction in the sky with almost exactly the same intensity, showing no variation whether the antenna pointed toward the galactic plane, toward open space, day or night, summer or winter. This uniformity was itself strange. Almost every source of radio noise they could imagine would be concentrated in some particular direction, toward the galaxy, toward the sun, toward some specific astronomical source. This hiss came from everywhere, equally all at once. What they did not know at the time was that a group of physicists at nearby Princeton University, led by Robert Dicke, working with Jim Peebles and others, were at that exact moment actively theorizing about exactly this kind of signal and were in the process of building their own instrument specifically to search for it. The Princeton team's reasoning traced back to an idea first developed decades earlier, most notably by physicist George Gamow and his colleagues in the 1940s. If the universe had indeed begun in an extremely hot, extremely dense state, as several independent lines of theoretical and observational evidence were, by the 1960s, increasingly suggesting, then the early universe would have been filled with an intense bath of thermal radiation. As the universe expanded over billions of years, that radiation would have cooled and stretched along with the expanding space itself, but it would never have disappeared entirely. It should still be detectable today, the theory predicted, as a faint, uniform glow of radio waves arriving from every direction in the sky simultaneously, the afterglow cooled by billions of years of cosmic expansion of the universe's own hot beginning. When a colleague put Penzias in contact with the Princeton group, both teams realized almost immediately what had happened. Penzias and Wilson, trying to solve a calibration problem with their antenna, had stumbled directly onto the very signal Dickey's team was carefully preparing to search for. The two groups published companion papers in 1965, Penzias and Wilson describing the puzzling excess noise they had measured, Dickey's team explaining in the paper immediately following it exactly what that noise almost certainly was. It was the afterglow of the Big Bang itself. The cosmic microwave background, photons that had been travelling, essentially undisturbed, for 13.4 billion years, since the moment the universe first became transparent to light. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. They had not set out to find evidence for the origin of the universe. They had set out to clean pigeon droppings out of an antenna and found instead the oldest light in existence, filling the entire sky, exactly as a small group of physicists in New Jersey had predicted it should. The discovery of the cosmic microwave background transformed the Big Bang from an intriguing theoretical proposal into one of the best-supported conclusions in the entire history of physics. But it was not, and has never been, the only line of evidence. What makes the Big Bang model so well established is the way several completely independent lines of evidence all converge on the same story. The first piece of evidence, chronologically, came from Edwin Hubble's 1929 discovery that we explored earlier in this series. Galaxies in every direction are moving away from us, with more distant galaxies receding faster than nearer ones. Run that observation backward in time, like reversing a film, and the implication becomes unavoidable. If everything is moving apart right now, then everything must have been closer together in the past. Trace it back far enough, and everything converges toward a single point, an extraordinarily hot, extraordinarily dense state, from which everything we now observe originated. The second piece of evidence is the cosmic microwave background itself, which we have just explored, the precise uniform afterglow of that hot early state, exactly matching the temperature and characteristics that theoretical calculations predicted it should have if the Big Bang model is correct. The third piece of evidence is one that deserves particular attention because it demonstrates something remarkable. The Big Bang model does not just describe the beginning of the universe in vague terms. It makes precise, falsifiable numerical predictions that can be directly tested. This third line of evidence is called Big Bang nucleosynthesis, and it concerns the specific chemical composition of the early universe. In the first few minutes after the Big Bang, a window of time cosmologists can calculate with remarkable precision, roughly between 1 second and 20 minutes after the beginning, the universe was hot and dense enough for nuclear fusion to occur throughout all of space simultaneously, briefly turning the entire universe into something resembling the interior of a star. During this narrow window, protons and neutrons fuse together to form the very lightest elements, hydrogen, helium, and small trace amounts of lithium. The Big Bang model makes a very specific quantitative prediction about exactly how much of each of these elements should have been produced during that brief window, based entirely on the physics of nuclear fusion and the conditions of the extremely early universe. It predicts that roughly 75% of the ordinary matter in the universe should be hydrogen, roughly 25% should be helium, and there should be only an extraordinarily tiny trace amount of lithium, figures calculated using nothing but well-established nuclear physics, entirely independent of any direct astronomical observation. When astronomers measure the actual composition of the oldest, most pristine matter they can find in the universe, gas clouds that have never been processed through the nuclear furnaces of stars, which would have altered their original composition, the measured proportions match the Big Bang model's predictions with remarkable precision. Roughly 75% hydrogen, roughly 25% helium, trace lithium in almost exactly the predicted quantity. This precise numerical agreement between a calculation made using nuclear physics alone and an entirely independent astronomical measurement is one of the most powerful pieces of evidence in all of modern cosmology. It is not merely consistent with the Big Bang model, it is difficult to imagine any other explanation that would produce that exact specific ratio of elements distributed uniformly throughout the observable universe. 3 completely independent lines of evidence. The expansion of galaxies, the cosmic microwave background, the precise chemical composition of the primordial universe. Each one arrived at through entirely different methods, using entirely different instruments, developed by entirely different groups of scientists across several decades. All 3 converge with remarkable precision on the same extraordinary conclusion. The universe began in an extremely hot, extremely dense state, approximately 13.8 billion years ago, and has been expanding and cooling ever since. This is why physicists speak of the Big Bang with such confidence. Not because it is a comfortable or intuitive idea, it is neither, but because the evidence for it is genuinely overwhelming, arrived at from multiple independent directions that all happen to agree. Here is where the story becomes considerably more interesting, and where the precision of modern cosmology runs directly into a hard physical limit. We can trace the history of the universe backward, using well-established physics to an extraordinary degree of precision, but there is a specific point beyond which direct observation, no matter how sophisticated our instruments become, simply cannot go. And understanding exactly why reveals something important about the nature of light itself. For the first 380,000 years of the universe's existence, as we touched on briefly in an earlier chapter of this series, the universe was not transparent. It existed as an extraordinarily hot, dense plasma, a churning, opaque sea of charged particles, primarily free electrons and atomic nuclei, not yet able to combine into stable, neutral atoms because the ambient temperature and energy were simply too high. In this state, photons, particles of light, could not travel freely. They were constantly scattering off the free electrons that filled all of space, absorbed and re-emitted in an endless, chaotic sequence, never travelling in a straight line for any meaningful distance before being deflected again. The early universe, in this sense, functioned somewhat like the interior of a thick fog or the inside of the sun itself, filled with light but opaque to it, because that light could not travel any meaningful distance without being scattered. This means that no telescope, regardless of how sensitive or sophisticated it becomes, will ever be able to directly observe anything from before this moment using light. The light itself simply could not travel freely enough during that earlier period to reach us intact, carrying reliable information about what was happening. It was trapped, scattering endlessly within the opaque plasma of the infant universe. At approximately 380,000 years after the Big Bang, this changed, in an event cosmologists call recombination. As the universe continued expanding, it continued cooling. Eventually, the temperature dropped low enough to around 3,000 degrees Kelvin for electrons and atomic nuclei to combine and form stable, neutral hydrogen and helium atoms for the first time. Once this happened, the free electrons that had been scattering light so relentlessly were suddenly, almost universally, absorbed into stable atomic orbits. The universe, essentially in a single cosmic instant, transitioned from an opaque plasma to a transparent gas. Light, for the first time in the universe's history, could travel freely without being constantly scattered. The photons released at that exact moment are precisely the cosmic microwave background, the same afterglow that Penzias and Wilson detected entirely by accident in 1964. Those photons have been travelling, essentially undisturbed, for the entire history of the universe since that moment, cooling and stretching as the space they travel through continues to expand until they finally reach our detectors today as faint microwave radiation corresponding to a temperature of just 2.7 degrees above absolute zero. This creates what cosmologists sometimes call a wall or a curtain at the very edge of what can ever be directly observed using light. We can see with extraordinary clarity all the way back to 380,000 years after the Big Bang. We can measure the precise properties of that ancient light with astonishing precision. The Planck satellite, which we discussed in an earlier chapter of this series, mapped it across the entire sky to a precision of better than 1 part in 100,000. But we cannot see any further back than that specific moment. Not because our telescopes are insufficiently powerful, because the light itself from any earlier period simply does not exist in a form that could ever reach us. It was scattered into incoherence before it ever had the chance to travel freely. Everything we know about the universe before that 380,000 year mark, everything about the first fraction of a second, the first minute, the first year, is not derived from direct observation. It is derived from something else entirely. Careful theoretical extrapolation built on the foundation of extraordinarily well-tested physics, reasoning backward from what we can observe toward what must have been true before it, using the same fundamental laws of physics that have been rigorously verified in laboratories and particle accelerators here on Earth. That distinction matters enormously for what comes next. Chapter 5. The first fraction of a second. Anomaly 2. Extrapolating beyond the wall. Given the wall of light we just described, how can physicists claim to know anything at all about the universe's first fraction of a second, the period cosmologists sometimes call, with a certain wry precision, the very early universe? The answer lies in the extraordinary predictive power of well-tested physical theories, applied carefully and honestly to conditions far more extreme than anything that can be directly recreated or observed, but governed, physicists have strong reason to believe, by the same fundamental laws that operate everywhere else. Consider an analogy. If you know precisely how a ball behaves when dropped from a rooftop, its acceleration, its trajectory, the exact physics governing its fall, you can calculate with confidence exactly where it would have been at any earlier point during its fall, even though you did not directly observe that earlier moment. You are not guessing. You are applying a thoroughly verified physical law to a situation you did not directly witness, and trusting the law to hold. This is, in essence, what cosmologists do when they reason about the universe's first fraction of a second, though the physics involved is dramatically more sophisticated, and the confidence in each specific claim varies considerably, depending on how well tested the relevant physics actually is at the energy scales involved. Working backward from what we can observe, physicists can describe the universe's history with reasonably high confidence back to approximately 1 second after the Big Bang, the point at which Big Bang nucleosynthesis, discussed a few chapters ago, began. The physics governing this era, primarily nuclear and particle physics, has been extensively tested in laboratories and particle accelerators here on Earth, giving physicists strong confidence in extrapolating it to the conditions of the very early universe. Pushing further back to around 100 billionth of a second after the Big Bang, physicists reach an era they can describe using the standard model of particle physics, the well-established framework describing the fundamental particles and forces of nature, extensively verified through decades of experiments at particle accelerators, including the Large Hadron Collider at CERN. At this stage, the universe would have been so hot that the 4 fundamental forces we observe today, gravity, electromagnetism, and the strong and weak nuclear forces, may have behaved quite differently than they do now, with electromagnetism and the weak nuclear force existing as a single, unified force that only separated into 2 distinct forces as the universe cooled. Push back further still, and the confidence of physicists in their models decreases considerably, though the theoretical frameworks become in some ways more remarkable. At around 10 to the negative 36 seconds after the Big Bang, a duration so brief it defies any everyday comparison, many cosmologists believe the universe underwent the period of extraordinarily rapid expansion we touched on in the previous chapter of this series, cosmic inflation, during which the universe is theorized to have expanded by an almost incomprehensible factor in an almost incomprehensibly brief span of time. And then there is the very beginning itself, the singularity, the moment often colloquially called time zero, at which all of the universe's matter and energy would have been compressed into a state of, according to a straightforward application of general relativity, infinite density, and infinite temperature. Here is where physicists become genuinely, carefully honest about the limits of what they actually know. General relativity, Einstein's extraordinarily successful theory of gravity, predicts this singularity when extrapolated all the way back to time zero. But general relativity is a theory that does not incorporate quantum mechanics, and virtually every physicist working in the field believes that at these extreme energy scales at which gravity itself should be operating according to quantum principles not yet properly understood or unified with existing quantum theory, general relativity's predictions can no longer be trusted. The honest, careful statement that most cosmologists would make if asked directly what happened at the very beginning, at time zero itself, is this: we do not know. General relativity predicts a singularity, but that prediction is almost certainly a sign that the theory has been pushed beyond the boundary of its own validity, not a reliable description of what was actually happening. A complete working theory of quantum gravity, combining general relativity with quantum mechanics in a way that no one has yet fully achieved, would presumably be required to describe that very first instant accurately. And no such theory currently exists in a form that has been experimentally confirmed. The Big Bang, in other words, describes with extraordinary confidence and precision everything from approximately 1 second after the beginning onward. It describes, with somewhat less certainty but still considerable confidence, the physics down to a tiny fraction of a second after the beginning, and at the very beginning itself, the singularity, time zero, it runs into exactly the same wall that general relativity runs into at the center of a black hole, a parallel we explored in an earlier chapter of this series. The mathematics simply stops producing meaningful answers. There is a specific and genuinely puzzling problem embedded within the basic Big Bang model that led physicists to develop the theory of cosmic inflation in the first place. And understanding this problem reveals something important about how the universe's structure came to be as uniform and orderly as we observe it to be. The problem has two related components, usually called the horizon problem and the flatness problem. The horizon problem concerns the extraordinary uniformity of the cosmic microwave background across the entire sky. When astronomers measure the temperature of that ancient light in one direction of the sky, and then measure it in the exact opposite direction, regions of space that, according to the standard Big Bang model without inflation, would never have had time to be in any kind of physical contact with each other given the finite speed of light and the finite age of the universe at the moment that light was released. They find the temperature matches to an extraordinary degree of precision, differing by only about 1 part in 100,000. This is genuinely strange. If two regions of the early universe were never in contact with one another, never close enough for light or any other physical influence to travel between them and allow them to reach the same temperature through ordinary physical processes, there is no obvious reason they should have ended up at almost exactly the same temperature. And yet, across the entire observable sky, they did. The flatness problem is related but distinct. It concerns the overall geometry of the universe, whether space itself is curved like the surface of a sphere or flat, like an idealized, perfectly level plane extending in all directions. Careful measurement shows that the universe's geometry is remarkably close to perfectly flat, to within the precision our best instruments can currently measure. But according to the standard Big Bang model without inflation, this precise flatness represents an extraordinarily unlikely, almost impossibly fine-tuned starting condition. Any small deviation from perfect flatness in the extremely early universe should have been dramatically amplified over billions of years of subsequent expansion, leaving the universe today either sharply curved in one direction or the other. The fact that it is not, the fact that it remains so close to perfectly flat after nearly 14 billion years of expansion, requires the initial conditions to have been tuned to an extraordinary, almost unbelievable degree of precision. Cosmic inflation, first proposed in the early 1980s by physicist Alan Guth, along with important subsequent contributions from Andre Linde, Paul Steinhardt and others, offers an elegant solution to both problems simultaneously. The theory proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion, far faster than the ordinary expansion that has continued ever since. During this period, a region of space small enough to have been in close physical contact, small enough to have reached a uniform temperature through ordinary physical processes, would have been stretched to a size vastly larger than the entire observable universe we see today. This single mechanism elegantly solves the horizon problem. The reason distant regions of the sky show the same temperature is that they were, in fact, in close physical contact before inflation began, and inflation simply stretched that already uniform region to an enormous size, carrying its uniformity along with it. The same mechanism resolves the flatness problem. Just as stretching the surface of a small balloon makes it appear increasingly flat to an observer standing on it, regardless of its original curvature, the extraordinarily rapid expansion of inflation would have flattened out any pre-existing curvature in the universe's geometry, leaving it extremely close to perfectly flat, regardless of what its curvature might have been before inflation began. Inflation is not merely a clever mathematical patch, invented after the fact to solve these two problems and nothing else. It makes additional, independently testable predictions, including specific quantitative predictions about the exact statistical pattern of tiny temperature fluctuations that should appear in the cosmic microwave background. These predictions have been tested with remarkable precision by satellites including Planck, and the observed pattern of fluctuations matches what inflationary theory predicts with impressive accuracy. This is why the majority of cosmologists currently accept some version of cosmic inflation as very likely to have occurred, despite the fact that it describes physics at energy scales far beyond anything that can be directly recreated or tested in a laboratory. It is not proven with the same overwhelming certainty as the basic Big Bang model itself, but it solves genuine serious problems and it makes testable predictions that have, so far, been repeatedly confirmed. And yet inflation, elegant as it is, raises its own uncomfortable question, one we touched on in the previous chapter of this series. What caused inflation to begin in the first place, and why did it end when and where it did? These questions remain genuinely, actively unresolved, sitting at the exact frontier of current cosmological research. Having traced the story of the universe's beginning as far as current physics can confidently take us, it is worth spending some time, carefully and honestly, with the questions that remain genuinely open, not as failures of the Big Bang model, but as the natural, honest frontier of an otherwise remarkably successful scientific theory. The first, and perhaps most fundamental open question is simply this: what caused the Big Bang itself? What, if anything, existed before it or caused it to occur? This question, phrased this way, may not even be well formed, given everything we have discussed tonight about the origin of time itself. If time began at the Big Bang, then the concept of before the Big Bang may be as meaningless as asking what lies north of the North Pole. Not a mystery awaiting a clever answer, but a question built on a false premise. An assumption that before must always be a meaningful concept, when in fact it may only be meaningful within a universe that already possesses a coherent notion of time. Some theoretical proposals attempt to address this question anyway, working within frameworks that do not necessarily assume time began at the Big Bang in the way the simplest version of the model suggests. Certain versions of string theory and loop quantum gravity, both serious, actively researched candidate frameworks for a complete theory of quantum gravity, propose scenarios in which the Big Bang was not an absolute beginning, but rather a transition, perhaps a rebound from a previous phase of cosmic contraction, sometimes called a big bounce, or perhaps a boundary within some larger, more encompassing structure of reality that current physics has not yet fully mapped out. None of these proposals has been confirmed by any observational evidence. They remain, honestly, speculative extensions of frameworks that are themselves still unconfirmed. But they represent serious, carefully reasoned attempts by working physicists to grapple with a question that the standard Big Bang model on its own does not and perhaps cannot answer. A second open question concerns what physicists sometimes call the initial conditions problem, closely related to inflation. Even if cosmic inflation successfully explains the specific uniformity and flatness we observe in the universe today, it does not, on its own, explain why inflation itself began or what specific physical mechanism triggered it in the first place. Various theoretical models propose different answers, involving hypothetical fields, sometimes called inflaton fields, with specific theoretical properties. But none has been experimentally confirmed, and the search for a complete satisfying answer remains an active area of theoretical research. A third, deeply strange open question concerns what is sometimes called the multiverse, a concept we touched on briefly in the previous chapter of this series when discussing eternal inflation. If inflation once begun does not necessarily end everywhere simultaneously, then our own observable universe might be just one region among an enormous, perhaps infinite number of similar regions, each forming its own separate, causally disconnected universe, each with potentially different fundamental physical constants, different laws, different histories. This remains a serious theoretical possibility that emerges naturally from certain well-regarded models of inflation, but it is not, and may never be, directly testable through observation, since by its very nature it describes regions of reality that lie permanently beyond our observable horizon. There is an honest tension worth acknowledging directly here, one that thoughtful physicists themselves openly discuss. Some of these proposals, particularly certain versions of the multiverse concept, are difficult to test in the traditional scientific sense, since they may make no predictions that could ever be verified or falsified through any observation we could ever perform. This has led to genuine, ongoing debate within the physics community itself about where, precisely, the boundary lies between legitimate theoretical physics, however speculative, and ideas that have drifted outside the bounds of what can properly be called testable science. That debate itself is worth taking seriously rather than glossing over. Not every mathematically elegant idea deserves to be treated as an established scientific fact, and the most intellectually honest position at this stage of the field is to hold these deeper speculative ideas about the ultimate origin of the Big Bang with considerably more tentative confidence than the well-established core of the Big Bang model itself. It is worth pausing to appreciate the specific, somewhat unusual history of how the Big Bang model came to be accepted, because the story reveals something important about how genuinely difficult, genuinely counterintuitive scientific ideas eventually earn their place as established fact. The term Big Bang itself has an interesting and slightly ironic origin. It was coined in 1949 by the astronomer Fred Hoyle, not as a term of endorsement, but as a dismissive label. Hoyle was one of the leading proponents of a rival theory called the steady-state model, which proposed that the universe had no beginning at all, that it had existed, essentially unchanged in its overall large-scale properties, for an infinite span of time, with new matter being continuously created to fill the gaps left by cosmic expansion, maintaining a constant, unchanging average density throughout all of time. Hoyle used the phrase Big Bang during a radio broadcast, intending it as a somewhat mocking description of what he considered an implausible and inelegant rival theory. The name stuck, adopted enthusiastically by the very scientists whose theory it had been coined to criticize, and has been the standard term ever since. A small, curious irony in the history of scientific language. For much of the mid-20th century, the Big Bang and steady-state models existed as genuine scientific rivals, each with serious credentialed proponents, each attempting to explain the same basic astronomical observations, most notably Hubble's discovery of the expanding universe, in fundamentally different ways. The discovery of the cosmic microwave background in 1964 effectively settled the debate. The steady-state model had no natural mechanism to predict or explain a uniform universe-filling background radiation with precisely the characteristics that Penzias and Wilson had detected. The Big Bang model, by contrast, had specifically predicted such a radiation should exist years before it was actually found, based purely on theoretical calculations about the early universe's temperature and density. This is worth sitting with directly because it represents scientific reasoning working exactly as it is meant to. A theory made a specific, falsifiable prediction in advance of any observation. A rival theory made no such prediction and had no natural way to accommodate the observation once it was made. When the observation was finally carried out, largely by accident by two researchers who were not even looking for it, it matched the first theory's prediction with remarkable precision and failed to match the second theory's expectations at all. Fred Hoyle himself, notably, never fully accepted the Big Bang model, continuing to develop and defend modified versions of steady-state cosmology until his death in 2001, decades after the vast majority of the scientific community had moved on. His persistent skepticism is sometimes cited today somewhat unfairly as an example of stubbornness in the face of overwhelming evidence. But it is worth remembering that Hoyle also made genuinely profound, lasting contributions to astrophysics during this same period, including foundational work explaining precisely how heavier elements are forged inside the nuclear furnaces of stars, the same physical process, incidentally, responsible for the carbon, oxygen, and calcium that make up your own body. The history of the Big Bang model, then, is not a story of a single, sudden, triumphant discovery. It is a story of decades of careful, competing theoretical work, tested rigorously against the mounting weight of accumulating evidence, with one model ultimately prevailing not through argument or authority, but through the steady, patient accumulation of independent, converging observational evidence that a genuine scientific rival simply could not adequately explain. There is something worth sitting with quietly as we come to the close of tonight's journey, something that goes beyond the specific physics we have carefully traced tonight. The universe, 13.8 billion years ago, began in a state so hot, so dense, so fundamentally different from anything we can directly experience or intuitively imagine that our best physical theories can only describe it up to a certain point, and then, with appropriate scientific humility, admit that they cannot go any further. And yet, from that almost unimaginable beginning through nearly 14 billion years of cooling, expansion, and the patient, unhurried work of gravity slowly assembling structure out of near-uniform chaos, something remarkable eventually emerged, matter capable of asking and beginning to answer exactly how it came to exist in the first place. Every atom in your body, every atom in this room, in this planet, in every star visible in the night sky, was present in some earlier form, within that first fraction of a second after the Big Bang. The hydrogen in your body's water is almost entirely primordial, forged during those first few minutes we discussed a few chapters ago, essentially unchanged in the billions of years since. The heavier elements, the carbon, the oxygen, the calcium in your bones, the iron in your blood, were forged later inside the nuclear furnaces of stars that lived and died long before our own sun ever ignited, exactly as Fred Hoyle's own foundational research helped establish. You are, in the most literal and precise sense that physics can offer, made of material that has existed, in one form or another, since almost the very beginning of time itself. The atoms that will tonight carry the thought of this sentence through your mind were present in that first, unimaginably hot instant, and have been continuously present, rearranging themselves through billions of years of cosmic history ever since. That is not merely a poetic observation, it is a literal, scientifically precise statement about your own physical composition, verified through decades of careful astrophysical research into stellar nucleosynthesis and Big Bang nucleosynthesis alike. Here is the thought I find myself returning to, again and again, when I sit with this particular mystery. The universe spent 13.8 billion years through processes with no discernible purpose or intention behind them, gravity pulling matter together, nuclear fusion igniting inside stars, chemistry slowly assembling increasingly complex molecules over unimaginable spans of time, eventually arranging a small portion of itself into a form capable of building radio telescopes, capable of noticing a persistent, puzzling hiss in an antenna, capable of tracing that faint signal back to the very beginning of everything. The universe did not have to produce anything capable of understanding its own origin, and yet, at least in this one small corner of an otherwise vast and largely indifferent cosmos, it did. We do not know what happened at the very first instant. We may never know, not with the same confidence we hold about everything from 1 second onward. That gap in our knowledge is not a failure of science. It is an honest acknowledgement of exactly where our best current theories reach their limit. A limit that may, one day, be pushed further outward by ideas not yet imagined, the way Einstein's relativity pushed beyond Newton, the way the Big Bang model itself pushed beyond a static, eternal universe that had seemed, to previous generations, simply and permanently obvious. 13.8 billion years ago, something happened that we still cannot fully explain, and from whatever that something was, everything else followed. Every galaxy, every star, every atom forged inside those stars, every planet those atoms eventually assembled into, and eventually on at least one of those planets, something capable of lying quietly in the dark, listening to this story and wondering in turn about the very beginning of everything. The universe began. We do not fully know how, but we are undeniably here to ask.